So welcome everyone, and thank you for coming to today's talk. I'm really happy to welcome everyone to today's session. So today's speaker is Ruoyu Lee. He's at the School of Astronomy and Space Sciences at Nanjing University. Is currently an associate professor there. So Ro is not a stranger. He's actually given a talk at the CDY Seminar series last year. He's an expert on particle acceleration, on cosmic rays, energetic transport, particle transport, and his interests are on high energy and ultra high energy cosmic rays, as well as high energy neutrinos and particle acceleration mechanisms in a vast range of sources. So Ruoyu got his PhD from the University of Heidelberg, during which time he was a fellow of the International Max Planck Research School for Astronomy and Cosmic Physics. And since then, he did a postdoctoral research position at Max Planck MPIK and also at DAISY. And currently, he's at Nanjing University. So let's welcome Ruoyu, and the title of his talk is Detection of Microquasars by LHAASO, which I think everyone here knows has been really exciting results that we have seen come out lately. So just a note, we will be recording the session, as I mentioned. It will go on our YouTube archives. If you're not speaking, please mute yourself. So Ruoyu, it'll be 50 minutes of speaking and then followed by questions, and then we can have a general discussion. So please be ready for participating. So thank you very much, and you can get started.
Okay, thank you, Rashmi, for the introduction. And good morning, good afternoon, and good evening, everyone. So I'm very glad to have this opportunity again to talk about the recent discovery of LHAASOs on behalf of the collaboration. So the paper you can find in archive with this ID number. And here, these are people I want to thank for the collaboration in these studies. Okay, so this is the outline of this talk. So since the previous two seminars are all about microquasars, so I will just give a very brief introduction of microquasars and the LHAASO experiment, and then I will talk about the LHAASO's discovery, LHAASO's observations of microquasars. I'll go through. We have five detection of five microquasars. I'll go through them one by one. Then I will discuss the implication of our findings and then give a summary. So first, microquasars as the particle accelerator. So microquasars are binaries with a mildly relativist jet. So the binary system can be composed of a compact object such as neutron star or a stellar mass black hole with a companion donor stars. So in this study, we mainly focus on the microquasar with this compact object being a black hole. So in this kind of systems, the radio observations, long-term radio observation has already proved that they are particle accelerators. But now the question that whether they are extreme particle accelerators, meaning whether they can accelerate particles to the energy around the knee or even beyond knee, let's say PeV or even 1000 PeV, called pivotron or super pivotrons. So in principle, there are several possible sites in this kind of system can be particle accelerators. Apparently, the jet, when the jet are terminated by the surrounding medium, there are strong terminator shocks which can accelerate particles. And in the accretion process can also launch powerful wind instead of in addition to jet. So this powerful wind, they can also drive shocks in the surrounding medium and also can be particle accelerators. Sometimes this, if the companion star are massive stars, then the massive stellar wind, the collision between massive stellar wind and the accretion wind or with interaction with the jet can also produce shocks. And also inside the jet, because when the jet propagates, it can interact with the surrounding medium, such as the cocoon or the wind, stellar wind, or the ambient ISM. then the jet velocity can perform a stratified profile. This means the central part can be faster than the boundary part. Then in this case, if particles are scattered among different layers of velocities inside the jet, the shear particle acceleration mechanism can work and boost particle to high energies. Also, there could be internal dissipations inside the jet, such as internal shocks or magnetic reconnections. Then this kind of dissipations can also energize particles. At the central part of this system, let's say close to a black hole, there are suggestions that if the fast rotating black hole has a magnetosphere, then the centrifugal force can also be a particle accelerator. There are also previous suggestions that the magnetic reconnection or strong turbulence may occur in the accretion disk, and this can also serve as the particle accelerator. So basically, there are many possible acceleration sites across different scales of the system. So now, yeah, the question is that whether, where, and how this extreme particle acceleration occurs, and to which energy these particles can be achieved in these systems. So, high energy gamma rays are usually considered as a probe of efficient particle acceleration. So, in this microquasar system, at the small scales, let's say within the binary orbit or close to the binary, there are intense radiation from the accretion disk, from the corona, from the companion star. This can be a good target for inverse Compton and also for the P-gamma interaction. And there are also dense matter in the accretion flow or in this stellar wind if the companion star is a massive star. And these are also good target for PP collisions, so they can reveal accelerated protons. At a large scale, although the radiation field and matter are not that dense, but still, let's say the CMB can be target for inverse Compton radiation, and the surrounding medium, such as the molecular cloud, atomic cloud close to the system, can also reveal relativistic protons via proton-proton collisions. So previous observations show microquasar has some high energy gamma emission from GeV to PeV band. So here we don't talk about the sequence X3. So because the central compact object is not confirmed to be a black hole. For these sources, in most of the cases, the emission are discovered in GeV to TeV band. They can appear as the sporadic emission or some kind. In some sources, they show this emission appear as a short time flares. And the recent discovery by LHAASO and Hawk show that SS463 and V4641 SGR are kind of stable TeV gamma emitter. So here, so this figure shows the LHAASO detection of SS463, and they find this energy dependent morphology. And based on this phenomenon, they suggest this emission are produced by inverse Compton of electrons accelerated at the jet terminations. This is, as we can see, this gamma emission are associated with the X-ray lobe, and this indicates the acceleration of about 100 TeV electrons in this jet termination sites. And very recently, Hawk also published their discovery of V4641. They find this extended or elongated radiation around this transient black hole X-binary transient, and they also find a possible indication of these two blobs at a different opposite direction with respect to the black hole. So So LHAASO, then let's talk about LHAASO. So although I think most of you are familiar with the instrument, but as a collaboration talk, I just still have to give a brief introduction. So LHAASO is the extensive air shower type gamma ray detector at a high altitude. So it has a very high duty cycle, almost 100% duty cycle. So it can monitor the sky all the time, and it has a large field of view. And with usually we will collect photons with zenith angle up to 50 degree. And if the source is very bright, then sometimes we can extend the zenith angle to even larger degree. Also, in LHAASO's instrument, because we have especially at energy above tens of TeV, because we have the muon detector, so it gives us a very high rejection power of the cosmic backgrounds. That makes it very sensitive. For gamma ray detection, so LHAASO are composed of two detectors. One is called the WCDA, which is at the center. It's a water pool here at the center part of the array. So the operating energy range is about 1 to 30 TeV. And at the outer region, we have this electron detector and muon detector composed of which is composing this KM2A detector, which works mainly in energy range of 20 TeV to a few PeV. The angular resolution of the instrument is 0.2 or 0.3 degree. So for galactic sources, usually they are extended sources. So this angular resolution is sufficient for to detect this, to resolve this kind of extended sources. So in earlier this year, we published our first catalog, including 19 sources. Among them, there are 43 sources are ultra energy gamma ray source, meaning with the emission with 4 sigma or larger than 4 sigma significance of emission above 100 TeV. And this catalog is based on data up to the end of July in 2022, yes. So far, now we have 2 more, almost 2.5 years data. So I think there are much more source discovered now. And so this figure shows the LHAASO's sensitivity. We see about 100 TeV, the sensitivity. This 1 year for point X source sensitivity reach a few times 10 to minus 14 ergs per second square centimeter per second. So now we have operated with the full array for more than 3 years. So this sensitivity can go down to kind of 10 to minus 14. So then with this very powerful detection capacity, we search for the sky. For this, we select that like this black hole. We select the microquasars with the black hole as the compact objects. So based on previous observations, there are total 12 such kind of sources in LHAASO's field of view, and then we collect all the data up to for KM2A. We collect all the data up to the end of January this year. And for most of sources, we consider the zenith angle less than 50 degrees. And for this V4641, we extended the because it's quite the declination is at a quite southern hemisphere. So we extend the zenith angle to 60 degrees. And for WCDA, we use the data to the end of May of this year. And so this table summarizes the main results of LHAASO. So we detect ultra energy gamma ray emission from the vicinity of SS463, V4641, and GRS 1915, MAX-CG 1820, and the Cygnus S1. For other 7 sources in the field of view, we do not find sufficient significance in the direction of these sources, so we give up limit. So for this detected 5 detected sources, the SS463 and V4641, GIS 1915 are resolved. in particularly for SN4C3, we at the energy below 100 TeV, we see the source can be composed into two point-like sources. Let's say marked as SN4C east and west here. And above 100 TeV, it shows an extended source located close to, with a centroid close to the position of the black hole. So V4641 and GIS1915 are extended sources, and the other two detected sources, J1820 and 661, are point-like sources. We do not resolve them. Also, you can see the significance is not very high. So currently they are unresolved sources, and so we give upper limit of these two sources. So one interesting thing is that we find all these 5 detected microquasars, or let's say the microquasars with associated with ultra energy gamma ray sources. They show persistent black hole activity or remarkable outburst of black holes in recent years. And other 7 microquasars do not show notable black hole activities in recent years. But we know that the cooling time particles responsible for ultra energy gamma emission is longer than kiloyears. So that is to say, most likely these recent outbursts or activities are not related to the detected emission. But this kind of correlation, is that just a coincidence, or it implies something? For example, like we can use the black hole's recent activity, let's say over past few decades, as a proxy of ultra energy gamma rays. So I will go back to this point later. But let's first go through these 5 detected sources one by one. So the first source I want to talk about is SN4C3, as has already detected the energy to a few TeV to a few tens of TeV. The source shows like have two lobes, well, in spatial coincident with the X-ray lobes. So in our detection, for example, in this figure, where we show the WCDA's measurement in 1 to 25 TeV, we also find the source can be described with these 2 point-like sources in with this position coincident with the HAAS, the 2 lobes of HAAS very well. And it goes to higher energy. For example, in this figure, in this KM2A's measurement in 25 to 100 TeV band. Although the entire region can also be described with 2 point-like, but we can see by eye that the source size in this loss source direction becomes bigger. It's kind of inflated, becomes bigger in this direction. And if we go to even higher energy, goes beyond 100 TeV, the source morphology changes. So we clearly see the emission as concentrate from the center part, and also the morphology is best described with the extended source. And we see the morphology seems to have the kind of similarity to the gas distribution in this region, which marked as this white contour. So we did a kind of a test for the best morphology. So we use this delta AIC to judge the goodness of fitting. So here we test, we compare one extended Gaussian model with a 2 point source model. So if delta AIC is less than -10, then it means it favors a Gaussian model. But if it's greater than -10, it favors 2 points like source model. So we see here clearly this delta AIC changes dramatically at energy above 100 TeV. So this means the origin of emission above 100 TeV could be different from that at the lower energies. We also try to put 2 point source plus a Gaussian source together to fit the morphology. But currently, in this case, we didn't find a significant improvement of TS value or the significance with using three sources together. Also, the source parameters are not converged in this case. So I think we need more data maybe to test whether we can resolve three sources together in the LHAASO detection. So this figure shows the spectrum. Shows the spectrum of LHAASO. So in SS463 region. So this red and blue symbols are the spectrum from of the east lobes and the west lobes respectively. And this black one shows the spectrum from the central region, about 100 TeV. So if we combine them together, as shown in this figure, and if we follow the HAASO conclusion that the low energy emission are from electrons, then we use the inverse Compton model to fit the data here. But in this case, the high energy at high energy part, the let's say above a few tens TeV, due to the Canini-Schiena effect, the spectrum becomes quite soft and cannot explain the data here. So even if we assume the maximum electron injection energy to 10 PeV, which is unrealistically high, still we see as shown in this red dashed curve, the resulting flux cannot explain the observed flux. So this gives us hint that there should be another component responsible for the high energy emission. This is consistent with this dramatic change in morphology. We can also consider a case that so let's say the Leptonic emission is consistent with the HAASO measurement. So let's show in this way. In case the HAASO actually has the spectrum measured by HAASO is a bit harder. It's small. The flux is lower, but the spectrum is a bit harder than LHAASO's measurement. But if you fit this with the Leptonic model, because the spectrum is harder, so this is kind of the emission. If you take sufficiently high maximum injection energy, is kind of can reach the level at 100 TeV, but still still we can see at high energy around 100 TeV there's a large inefficient flux predicted by this inverse Compton model. So in this case we think there should be another component. So here this figure shows the this contour, green contour is the LHAASO's contour above 100 TeV. And this map is the Arecibo's H1 emission. So from this figure, the x-axis is the velocity of the atomic line, and at the distance of SS463, we see there is an axis here. So and this figure shows the gas kind of represents the gas distribution at the distance comparable to SS463, and the total mass within LHAASO's source region is about 25,000 solar mass, and the average gas density, atomic density inside the LHAASO region is about 30 per cc. So in this case, we perform a phenomenological modeling. We just use a Leptonic model to fit the low energy emission, and then we inject protons from the center of the source and let it diffuse in the surrounding medium, and we put we can adjust the distance of we put the atomic cloud a few tens of parsecond or a few hundred parsecond away from the black hole. Then by adjusting the parameters, we can get such kind of hadronic emission that the low energy protons have not reached the atomic cloud, but the high energy because the high energy protons, because they have faster diffusion coefficient, so they can reach the cloud and produce this ultra energy gamma emission in this case. So in such kind of scenario, the total injection luminosity of protons is about 10 to 39 x per second, which is possible for SS463 because the jets and also the disk wind discovered from this system all have kinetic energy, kinetic luminosity over 10 to 39 x per second, and the total luminosity above 100 PeV about 1 PeV is like 10 to 38 ergs per second. So we can also investigate into another scenario that let's first ignore this low energy the leptonic contribution. So if we fit all the spectrum here with the hadronic emission, then in total we need kind of 5 times 10 to 50 erg energy in protons above 1 GeV. So if there's kind of so this is obtained with the assuming the spectrum injection spectrum the spectrum to be minus 2.5 from 1 GeV to highest energy. So if there is kind of a break at the low energies, so the required energy can be smaller. So in principle, so we want to show that the morphology change and also the spectrum measurement of LHAASO together with this the H1 the distribution of H1 gas atomic gas actually support a hadronic arranging for ultra energy gamma emission from SS4CH3. These are just a phenomenological fitting, and so recently Parity et al. Have put a paper on arXiv for they provide a detailed model for particle acceleration in SS4CH3. So one can refer to this paper. Of course, I think there are other interpretation other than this paper for the emission in this region. Okay, then for V4641, so this LHAASO's morphology above 25 TeV, you can compare it with the Hawks detection, and also has the preliminary observation. And we see that LHAASO also find elongated structure in this region. But in the paper, we simply use Gaussian, a symmetrical Gaussian model to get to extract the signal and leave the further detailed study in the future. What's interesting is that the spectrum measured by LHAASO continues up to 800 TeV, and we didn't see a clear cutoff in this region. So this means the V4641 to be a very extreme particle accelerator, and if the emission are hadronic, then V4641 to be a super pivotal. This here is a test for a more complex source model here. So we also tried 2 point-like source model. In this case, we can also fit the source with 2 source, one above the black hole position, one below the black hole's position, similar to Hawks tried in their paper. We also tried using this rectangular to fit the morphology. Also, we use elliptical Gaussian to fit the swarm. Actually, the results are quite similar. You see, they are resulting in more or less same TS value. Considering the number of free parameters, so currently maybe the best model is this rectangular one. And also the source size is comparable with this measured by Hess, but with a little bit, I think it's a little bit longer in this direction. But generally it's comparable considering the error. So there are some possible interpretation of the 4641's emission. For example, in Hawks' paper, they consider there could be a large-scale jet in this direction. The jet can there could be like similar to SS4C3, there could be kind of jet terminations and the particle accelerate there and produce this emission above and below the black hole. But there could also be kind of particle accelerate here and diffuse into the surrounding region and produce this bubble-like structure. In another recent paper by Andrei and Dmitry, they proposed that this elongated structure actually reflects the large-scale structure of a galactic magnetic field, because given the position of this microquasar in our galaxy, the regular magnetic fields of our galaxy seems to be the projection of the magnetic field seems to be elongated, aligned with this direction of the source. So they claim this could be reflect the diffusion of accelerated particles along this regular magnetic field and produce such kind of elongated structure. So here I just want to say that although the spectrum goes to like 800 TeV, I think we cannot directly presume this emission to be hadronic, because if we assume a very hard electron injection spectrum with a hard maximum energy, then actually the spectrum can be fit very well in this case. For example, the shear acceleration, if let's say we have kind of a jet in this direction, and the shear acceleration can work and can produce this hard spectrum without any problem. So in this case, I think we need a deep X-ray and atomic or molecular line observations in this region to finalize, to determine the radiation mechanism of the emission of VE4641. For example, in this lemmatonic scenario, we can predict quite strong X-ray emission in as shown here. So I think this like XM Newton's observation will be crucial to differentiate different radiation mechanism of this source. Another next one is this GIS 1915. So this source is an extended source here, and the spectrum we see is consistent with the power law, goes up to 300 TeV, and we also didn't see clear cutoff feature in this source. So in principle, we can extend it to even higher energies. This region actually is a kind of a crowded region because it has many other sources in the surrounding medium, sorry, in the surrounding region. So here there is an energetic pulsar. We can resolve one point-like source around this region, and in this figure we have removed the source. And also in the southern region there is another energetic pulsar, J1913. This where this has detected this J1912 is extended source around this pulsar. And in this figure, we also removed this kind of source. And then we also have previously the GeV observation reveal an SNR G45 in this region, shown with this white circle. And here is a dense molecular cloud in this region, which is likely to be illuminated by particles escaping from the SNR. So although there are so many energetic potential particle accelerators, so GIS 1915 is the most promising one, most the closest one to the LHAASO source detected in this region. So this figure shows this GeV detection of the source in this region, and yeah, this is the HAAS observation. So this HAAS source has a quite large angular distance from this source around the GIS 1915. So it's less likely to be this emission here is come from this pulsar. So this figure shows the this is in galactic coordinates. So this is the superlunar remnant G45, and here are the source W shown here. This color shows the molecular gas in the same distance with the superlunar remnant, and this orange cross shows the position of LHAASO source, the centroid of LHAASO source. So we see the gas, the molecular gas is not coincident with the LHAASO's position. So here actually we see there's not much gas here. So the emission around the GI-1915 is also not likely coming from the particles accelerated by the SNR. And a recent paper by Laura, they show a possible GeV counterpart around the GI-1915. So they have subtract the emission from the SNR and the source W, and they find there's a residue here source close to GI-1915. So if we put the this GeV source, the spectrum GeV source here together with the LHAASO points here, we see they are not in the same power law. If they are from the same, if they have the same origin, then we could expect kind of a very sharp break somewhere around this maybe a few TeV here. So whether this source is the counterpart of GI-1915, so I think they need more investigation. So there are some interesting implication from radio observation of this in GI-1915 region. So previous observation by ARMA discovered two hotspots at different direction, opposite direction with respect to the central black hole. These two hotspots are considered as the possible jet terminator sites, and the particles can be accelerated here and produce the high energy emission. And this is the image from a recent talk in this Leonardo meeting. So they show that at here around this hotspot there are kind of this kind of ring-like structure, which could be which is suggested to be a bubble or ball shock inflated by the jet launched from GI-1915. So this could be a good acceleration site of particles, and also the size of the hotspot to the center is about 0.3 degree, which is consistent with the extension of LHAASO source. We also checked the gas distribution in this region at a distance of GI-1915, which is 9.4 kiloparsecond. So in this region, actually there are some kind of excess of gas here, and if we take the slice of the gas distribution with this velocity, we see such kind of structure. So this red one is the position of the black hole, and this cyan circle is the LHAASO source. Well, actually, we see the excess of the gas is not at the center of the LHAASO source, but still within this circle, there are the total gas mass, molecular gas mass is about 1.6 times 10 to 5 solar mass. So it's quite huge, and this leads to an average density, gas density to be 5 per cc. And so if we explain, if we want to explain the last matter spectrum with this gas density, then we need a kind of 4 times 10 to 48 erg energy in protons above 200 TeV, which is possible for this system. So I think we need to further study to distinguish the two scenarios. The one is like the LHAASO detection is from two unresolved lobes, as that in SS463, but it's because of the large distance the LHAASO does not resolve it. Or it could be the diffuse emission produced by the diffusing escaping protons from the system and in the surrounding medium. Then the two other sources are this MaxCG 1820 and the Cygnus S1. These two sources are all point-like sources. Although interestingly, so they have some in radio observation there show some connection with the LHAASO emission with this with the jet. So in first, let's say in J1820. So this black hole is discovered in 2018 in X-ray when it undergoes the X-ray outburst. So this meerkat's observation of the radio ejector from the black hole during the outburst. We see approaching jets in this direction and a receding jet in this direction. If we put it into this figure, we show the jets. So here is the this shows the approaching jet, and here's the receding jet. And we see LHAASO's source has kind of offset from the black hole's position, but it is consistent with the direction of the receding jet in this direction. And here we show the spectrum mirrored by LHAASO. In CDHY-1, this radio observation shows there is kind of a bubble-like structure. It's a ring. It's a ring in this region. The authors suggest this ring-like structure is a bubble inflated by a dark jet launched from CDHY-1. And LHAASO's source also has the offset from the position of the black hole, but it's consistent with the position of top of this ring structure here. So this makes it possible as from the particles accelerated by this bubble. Okay, so this here shows the 7 undetected microquasars. Here shows we can only give the upper limit of their spectrum. But from the morphology, actually, we see around some microquasars there's kind of a tentative emission with like 2 sigma level. So this microquasar may not be. I mean, it's. So the undetection of ultra-energy gamma ray from this microquasar does not mean they are not high energy particle accelerator. It could be just the injected the injection luminosity of particles is low, so we have not detected them. So we need more exposure to probably we can also detect some signal from some of them. And now I want to go back to the previous discussion for the possible connection between black hole activity and ultra-energy gamma emissions. So from this 5 detected microquasars, so SS463 and CDHY are persistent source, and GIS 1915 shows is active for decades, and although it has already entered a dim state in X-ray band, but still exhibit very frequent and bright radio flares. And V4641 is the one with the highest, shows the highest frequency of outburst among all these transient black hole X binaries. Also, this MAXI G1820 shows a major outburst in 2018. For other 7 undetected microquasars, we show we can see that there have not been outbursts detected since quite long time ago. So maybe this V444, the last outburst is in 2015. So this still close, only have nine years so far, but others have been silent for many years. On the other hand, we can see the particle cooling time. For proton cooling time, is determined by the gas density if we consider PP collision. So if let's take gas density to be 10 per cc, then the cooling time scale is 4 million years. So electrons cool more efficiently, but still it requires kind of long cooling time. So we see. So here shows the time scale of different process as a function of electron energy. So if we assume 3 microgauss magnetic field, then particles, let's say, have several hundred TeV, electron of several hundred TeV has a cooling time of several thousand years. Even if we take 10 microgauss magnetic field, still the cooling time scale need be 100 years. So in that case, it means this recent activities outburst of this black holes, they cannot need to the radiation of detected photons because the particles do not have sufficient time to cool. So they must accumulate. The particles responsible for the emission must have been accumulated for at least let's say 100 years, 1,000 years. Then there's a question. So is such kind of a correlation between black holes' recent activity and ultra energy gamma emission is it a coincidence? So if it is not a coincidence, then the duty cycle of black hole extra-binaries inferred from recent observations of recent decades, maybe they may reflect the energy release over this binary system in past 1,100 years. So it means we can use the recent activities of these black holes as a proxy for a longer term activities, let's say back to 1,000 years ago or even 10,000 years ago. Actually, this kind of this period of time is not long compared to the life of this binary system. But if this apparent association is just a coincidence, then we should expect the ultra energy emission from other quiescent black hole extra-binary, because the current state does not mean the historical activity. There could be quite strong injection from past. Then they can the particles can be accumulated around the source and produce the emission so far. So in this case, we would expect the ultra energy emission from this quiescent black hole binaries, or even those undetected system. In that case, for example, there are some undetected sources in LHAASO's catalog. Then possible some of them could be come from some this black hole binaries. But in this case, we need some method to identify them as a counterpart of black hole binaries. There are also other factors can influencing the detection. For example, the fractional energy goes into long-thermal particles, because during outburst there are quite strong thermal emission in X-ray band. So then how much energy goes from this gravitational energy go to the long-thermal particle energy? So if there is no outburst, if there are no strong shocks or this or magnetic reconnection, such kind of vibrant process occurs during this process, then probably particles, the energy are just released in a thermal radiation. They are not, they will not show as the ultra energy emission. They will not go to high energy particles. And also there are other properties of the binary system themselves can influence the energy dissipation process. For example, there are suggestions that these outbursts are due to the disk instabilities, and which is related to the mass transfer rate from the companion star to the accretion disk. So these are complex processes, and so I think maybe there's not such a straightforward connection. Also, another thing that the radiation efficiency. For example, if there are dense gas appear around the microquasar system, so that they can reveal these protons, or there are, or if the turbulence is strong enough in the surrounding medium to trap accelerated particles therein, so that they can accumulate sufficient particle number and give a sufficient flux, detectable flux. So I think these are we need to study in the future. Another thing is that if we take the SS433 as a proxy, as a representative PeV particle accelerator, based on our previous modeling, we see to explain the emission above 100 TeV, we need a proton injection above 1 PeV proton injection with a luminosity of 10 to 38 arcs per second. So with this kind of luminosity, then we apply this simple leaky box model. We can estimate the PeV cosmic flux contributed by SS433 and similar sources. because according to the population study of black hole experiments in our galaxy, there is expected to be like 1,000 such kind of system in our galaxies. And there could be a dozen of them, probably boasting the extreme luminosity exceeding 10 to 39 ergs per second, which is similar to SF-43. So if, let's say that in our galaxy, there are the total PeV proton injection luminosity from this kind of extreme, very bright microquasars to be 10 to 30 ergs, 10 to 39 ergs per second, then the resulting PeV proton flux would be this value, which is consistent with the PeV flux measured, PeV proton flux measured by Cascada. Also, in a recent study by Guinel and Dimitri, they show that the PeV flux distribution in our galaxy could be quite patchy and quite time variable because the source number is quite rare. And in this case, the total injection luminosity could be as low as 10 to 38 erg per second to explain the observed flux at Earth. So this just want to so what we would just want to show that so microquasars, if let's take SF-43 as a representative microquasar, they are quite sufficient to explain the PeV proton flux measured at Earth. And another implication is for particle acceleration at the AGN, which has the kind of stronger jet and a more powerful jet. And also the acceleration size is also bigger. So from the point of view of the HELAASO condition, from the confinement condition, they can also accelerate. They could even accelerate particles to even higher energy, and maybe a potential candidate for ultra energy cosmic rays. Okay, so let me in a few minutes I'll talk about the future of these studies. So we plan to build this image aerotelescope telescopes in LHAASO site. So there we suggest we plan to build this 32 telescopes. Here with the telescope, each telescope will have a 6-meter mirror in diameters. So this project is already funded, and we now we are building these telescopes. The angular resolution of this this array can reach like 0.05 degrees. So this gives us sufficient power to resolve this LHAASO detected sources around the microquasars. Probably we can have better with this detection, we have a better understanding of the nature of this ultra energy gamma ray emission. So this telescope will be completed in 2028. So like say 4 years later. So another plan is to build this very big high energy underwater neutrino telescope with the total 30 cubic kilometers. So now we have like 2 candidate sites, one is the Lake Baikal and another is in Southern China Sea. And we have already have this some prototype in test. And this is this figure shows the estimated sensitivity of this neutrino detector. And we can see assuming E2-2 spectrum, the sensitivity can as low as like 10 to minus 13. So with such kind of detector, we can detect. I mean, if we 4641 is a hadronic arranging, then we can detect the neutrino signal from this source maybe less than 10 years. So this can give us a smoking gun for the radiation mechanism, the ultra energy emission from this system. Okay, so I'll just leave my summary here. Thank you very much for your attention.
Thank you, Ruoyu. Thank you very much. So there's time for questions. So please raise your hands. Susumu, why don't you go first?
Yeah. Hi, Roy. First of all, congratulations for the fantastic results. These are most exciting results from LHAASO yet, in my opinion. So question about their microquasars as pevitrons, I mean, sources of cosmic rays. So there was the discussion in the Hess paper for SS433 that cosmic rays from SS433 themselves itself cannot have contributed, or it is unlikely to have contributed, because the propagation time of the distance of 5 kiloparsecs is longer than the estimated lifetime. So I see that V4641 and GRS 1915 are even more distant. Maybe the nearest sources are Cygnus X1 and the Maxi source. I don't know what the lifetime constraints are for those sources, but could some of them actually have contributed to the cosmic ray PV cosmic ray flux at Earth?
No. Actually, we are not saying these sources are contributors of cosmic rays detected now at Earth. But what we want to demonstrate is that this kind of system, they have capacity to accelerate PV particles or even higher energy particles. And so there could be like past some historical binary system with the same powerful particle acceleration capacity. They can contribute to the mirrored cosmic rays at Earth.
Yeah, okay. So more nearby sources that maybe have ceased their activity by now. Probably. Is that, yeah, okay. Yeah, thanks.
Valenti, you're next.
Okay, thank you, Rashmi. Thanks a lot, Ruoyu, for this nice talk. I wanted to make 2 quick comments. One is related. Can you hear me properly?
Yes.
Great, thank you. One is related to V4641, because in LHAASO it's not obvious, but in the case of HAWK, and in particular the Hess results show this peculiar shape, which, well, at least visually looks peculiar. And also the different length of the 2 sides with respect of the structure with respect to the location of the binary. This is also clear in your results. So I wanted to point out that there might be significant proper motion of this system. So if one looks at the Gaia proper motion data, it could be a relevant factor shaping the large-scale interaction with the medium. So I wanted to mention that. And the other thing I wanted to mention related to GRS 1915 is the location of these radio hotspots, which sometimes are attributed to the potential termination of the jets. Putting aside, I think we had this discussion recently, putting aside that the luminosity they derive for these jets is very low. Beside that, also these hotspots are extremely small compared to the actual typical size of the structure. This region with this bow shock should be of arc minutes size, because the typical size of the whole thing. So it doesn't look very much like an actual termination shock.
Okay.
And that's it. I don't know if you want to comment on that, but I wanted to mention these 2 things. Thank you.
Yeah, I want to ask about the proper motion you mentioned. So you mean this kind of elongated structure could be a result of a proper motion? Is that, do I understand correctly?
Yes.
Well,
No, not elongated the structure, but the fact that the binary seems to be closer to the top of I don't know how to express it, but you see that it's not centered. The binary is not centered in your.
Yes.
And
okay,
this would be related to that.
So how fast is the speed, the proper motion speed?
Actually, I don't remember very well, but I was quickly checking the typical velocity from proper motion, and I got something of the order of 100 to 100 kilometers per second, if I didn't make a mistake. And actually, if you use typical parameters for the large scale structure, for the jet power and the time, the age of the source, you may get something which is a bit lower. So if your expansion velocity is lower than your proper motion, then the shape of the structure starts to be dominated by proper motion of the injector, and the thing becomes not so symmetric anymore.
Okay, thanks.
Thank you.
Thanks, Valenti. Laura?
Hi, hopefully you can hear me.
Yeah.
Thanks for the very nice talk. That was really great. Also great results. I wanted to ask about the sort of I know that you didn't make a very firm connection between like the flaring state or like recent activity of the sources and whether they emit in gamma rays. And I was wondering if you've considered something, because looking at your list, I find it honestly rather unconvincing to quote burst in 2018 as recent, but not one in 2015, right? Because it's like there's nothing special about 2016 somehow. And so I was wondering if you've looked into like more characteristics of this activity, like some kind of like flux threshold, or like, I don't remember from the top of my head, like how far away is V404 Cygni, like, would it still be consistent with your picture and it's simply somehow not detectable yet by LHAASO? Like, can you talk a bit more about this?
So you mean here? This is the figure sky map for V404 Cygni. Well, actually, you can see from the table, this Cygni it has very quite low significance. But well, I think one possibility is that for example, this nearby source, they have kind of how do you say, they have because currently we model this source all using kind of a pointer-like source or Gaussian this symmetric source. But if this source can kind of have some irregular morphology, so using the current source model, we could over subtract their emission, and in that case, it may be possible that we underestimate the significance here. So I think this we can do a more detailed examination for in this analysis. But currently, based on the standard method, we didn't find significance emission associated with V404.
Okay, thanks.
Sabrina, did you have a question?
Yeah, I had a question. Then I don't know. Hi, Ruoyu. Thank you very much for your talk. Very nice. Very nice. I have a question. Did you if you show the spectrum of SS433, so did you thought why you get higher flux with respect to HAAS? Is it so because it is 1908, very close by?
No,
how did you exclude 1908?
Yeah, so first, I think this difference could be the different strategy of taking a background. For example, I read a LHAASO paper, but if I remember correctly, so I think Laura here, she can correct me if I say something wrong. I think they take a background region in the surrounding region, not far from the SS433. So from this figure, although I understand that although the PSF or LHAASO is big, so this could be point-like source. But if there are some extended emission, diffuse emission in this region, then the background could the background in LHAASO analysis could be overestimated, and in that sense, the obtained flux can be underestimated. This is one possible reason. And for the contamination from 1908, yeah, here. So this is the region of this 10 times 10 degree RY, and SS433 is somewhere here. And we did this analysis of the entire region by using this 3D likelihood method. And so this is the final residue map. We see there's it's quite clean, and the how to say the counts. They follow this the normal. Yes. So also I think above 100 TeV, like the LHAASO's this angular resolution is like kind of 0.2 degree. So for G1908, this possible accelerator, such as this pulsar J1907. Actually, I think this is quite far from the position of SS43 with respect to this angular resolution. So I think it's not likely that this emission here is contaminated by J1908.
Okay.
Yeah, but yeah, I mean, this need to be continuously to check to be checked. Yeah.
Yeah, also because also Hawk data is a bit lower. Maybe it's it's very compatible with HAAS result data point. Yeah.
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 But,
Hi. Sorry to interrupt. I just wanted to because you mentioned the comparison with HAAS, and I wanted to say that I mean we derive the background from the similar region, but the exclusion region, so the region where we don't do that, is very large compared to the emission from SS43. And also the Hawk emission is consistent with HAAS, and Hawk has a completely different, like Hawk, there is no such a thing. And I was curious, I just wanted to say in the slide that you were showing before with the residual, do you have that but below 25 TeV? Because that's where the disagreement comes. Because I didn't see.
Okay, let me see.
Because above 25
so
TeV.
This is for
there,
25 TeV, above 25 TeV.
Below
yes.
20, and so but the disagreement is below 25 TeV. So do you have that?
No. I don't have my slides.
Okay.
Sorry.
Okay.
Yeah, but
sorry.
we can check. Yeah. Yes.
Okay.
But I think another thing is that the sensitivity, I think, is another important factor, because let's say if our let's say if the source is weaker, then probably we can only determine detect the hottest spot, right? The hot spot, the brightest region of the source, and we could miss the surrounding part. So I mean, this difference is understandable, because I mean, LHAASO has a higher sensitivity here. So we probably some kind of diffuse emitter we can recognize them and include them in our analysis. But if let's say if the source is weaker, then we cannot see this outer part. Then we would only extract the photon from this very center region. Then this will give a lower flux. Yeah, this is my. I think this could be also one possibility.
Thank you.
Jamie, you had a hand up for a while. So sorry, just go ahead.
No worries, thanks. I'll add my thanks for the talk as well. That was great.
Thank you.
I just have one question. I don't really know myself how complete the microquasar catalog in general is. I guess it's not terribly complete because some of these objects have been detected quite recently. But that leads to the question, is it possible that some of the unidentified LHAASO sources are associated with microquasars that have not yet been established to be microquasars?
Yeah.
And I'm wondering about things like the peculiar sources, LHAASO sources that are associated with that have been potentially associated with the millisecond pulsar, for example.
Millisecond pulsar. Okay. First, let me answer your first question. So I totally agree with you. I mean this kind of association, if they are just a coincidence, then I think it's very reasonable to expect some some X-ray black hole X binary, which is now in quiescent state. It could be ultra energy gamma ray emitter, or even some unidentified, undiscovered black hole in our galaxy could be ultra energy gamma ray emitter. But to identify, to connect this kind of astrophysical object with the LHAASO detected source is quite difficult. One possibility is that if we can detect their if we can identify their companion star via this we can, for example, from this Doppler effect of their emission lines, we see they are like kind of rotating with some very massive object. And in that case, so probably it provides an indication of the existence of the quiescent black hole in that case. But I think that would be very difficult to connect this kind of stuff, this kind of system to LHAASO. And for millisecond pulsar, yes, we have detection. But the paper is being prepared on the preparation, so I cannot talk more about that.
Okay, thank you.
Thank you.
Thank you. Other questions? Actually, while we wait for other questions, if you could go back to that to the slide where you showed the HES spectra and the LHAASO spectra one more time.
Yes.
Not this, yeah, yes, this one. So if I understand correctly, what you were saying is that the pink data points here are HES,
Yes.
right?
Yes.
And so the difference between the two plots, could you just say that one more time? I mean, basically I guess this is what you're talking about, the HES not being consistent with LHAASO. So maybe you have some diffuse emission in the LHAASO spectra?
Yes, I think. Yeah, I think there are several possibilities. First, the source, this blob itself, kind of has kind of extension, but at the outer region, the blob, the emission becomes quite weak. So if because LHAASO has higher sensitivity, so this weaker outer region are detected. So and we can collect the photons from this region. And when we get a higher flux, so this is one possibility. Another is that some due to some background subtraction strategy could be different. But as Laura just said, so HAWK has the same kind of strategy with LHAASO in background subtraction, and they also find kind of a bit slow, a bit lower flux. So I think maybe it's still due to the sensitivity. Yeah, so there are kind of some diffuse emission in the surrounding region.
Yeah, and Sabrina just put in the chat that the HAWK data points are compatible with HES. So that's useful. Okay, thank you. Svi, please go ahead.
Thanks for the very nice talk. Actually, I have two questions. One is about the energy budget. I'm a bit puzzled that so much energy, such a large fraction of the energy is coming out in PEV. So maybe I didn't understand it properly, but can you repeat, for example, the energy budget of SS433 in PEV compared to other energy, total energy, and so on? So this is the first question. And
sorry,
the second question.
Do you mean this slide, or energy budget, or which source? Sorry, I didn't hear you clearly.
I think where you were talking about the energy, the 10 to the 50 ergs of energy calculation that you were doing.
I'm talking about total energy emitted in PEV compared to total energy emitted in other bands.
You mean here?
The 38 versus 10 to 39 ergs.
Yeah.
Yeah, this is the slide, I think.
Yeah. So this value is obtained assuming a single power law spectrum of protons goes from 1 GeV to, let's say, a few PeV. So and this also depends on the gas density assumed here. Of course, I think this will not have a very big difference. But if we have a low energy break.
So I'm a bit surprised that so much energy is coming out at such high energy band, because it must be a significant fraction of the total energy budget of the system.
Okay, so this energy is for proton above 1 GeV.
I think there's a slight lag. So Svi, could you repeat your question, and then Ruoyu, you just wait before you respond.
Yeah, sorry, could you repeat?
Yeah, I had the same question. So it's surprising to maybe several of us that the luminosity in protons above 1 PeV is 10% of the total luminosity, maybe, of the source. People talk about 10 to the 39, 10 to the 40 ergs for total bolometric luminosity of SS43.
Okay, it's your point. So here is because I use a kind of a hard spectrum, hard injection spectrum here. Yes, so it depends on the spectrum shape you assumed. If this with a harder spectrum, because the most energy concentrated at the around this cutoff energy. So so in this case you can get very a large fraction of this PeV proton with respect to all energy.
And is there a lower bound on that? Because I guess most shock acceleration people get 10% or less for efficiency. It seems very strange everything's going into a PV. Can you drop that?
Well, I mean, as long as the the spectrum is not too soft. For example, if we just even we assume this flat spectrum, let's say SP equal to 2, we still can get kind of like 5% energy above at the highest energy range.
Wow.
Yeah, I mean, because for example, if you accelerate particle from 1 GeV to a few PeV, and then this maybe we count the highest energy from, let's say, about a few PeV, that it takes a half decades. Because with the -2 spectrum, then at each decade the energy is the same. So this gives you kind of 10% or 5% energy in this high energy band, high energy range.
Okay. Wow. Yeah. Okay, that's pretty
amazing.
But
I mean, but here is I just want to mention this is just a phenomenological calculation. So the purpose is that to show that in principle we can have a second kind of component to explain the data here with the hadronic overranging.
Yeah. And if you use that as an argument, the hadronic model must be wrong, then it's pretty impossible. Like, same thing happens in AGN. If you put hadrons, you need a lot of power, which maybe isn't so reasonable, but there's no way to explain it with electrons. Because the cutoff, but if you change the field, let's see. Yeah, because in AGN, for example, the luminosity, if you put in protons, is like much more than Eddington luminosity. So it's not so likely to be what we see for gamma rays. But and so that's an argument that maybe hadronic models are not so favored. But in this case, so is leptonic totally ruled out, and would that solve the energy problem if such a problem exists? So you want to decrease the efficiency of non-thermal acceleration that you infer from the observations. Is that?
I mean, from you mean the comparison with the AGN, the scenario?
Yeah.
But I mean, for AGN, we cannot assess such high energies, right?
No.
So
exactly, yeah.
Yeah. So basically, they are like to 10 TeV, and it's quite high because you know due to this EBR absorption.
Yeah.
So I mean, it's possible that if we can detect the spectrum of AGN to higher energies, then probably we can also see some contribution from hadronic process. I mean, just a guess.
Okay, thanks very much. Yeah, Pasquale. Yeah, sorry, and then.
I just wanted to follow up again on this issue. It's not clear to me. So are you saying that the luminosity of the jet is larger than 10 to 40 ergs per second?
The jet, I think the jet luminosity is a few times 10 to the 39. And also,
okay, but that means that there is an issue with the efficiency of the particle acceleration. It doesn't matter where you put this energy, but still you are requiring like 30, 40, 50% efficiency for the acceleration process. But it's actually, am I correct in saying that it's actually much worse than that? Because you mentioned that the hard spectrum that we see in your figure, like E to minus whatever, 1.8 or something, might be due to the fact that protons didn't reach out to the cloud yet. But that doesn't mean that they have not been accelerated. So the actual budget needs to be calculated where the particles are, not where they aren't. So you shouldn't integrate on the spectrum of the particles you see. You should be integrating on the spectrum of the particles that the accelerator injected, and that becomes much worse than this.
So here this value, this is the injection index. So in this calculation, we include the propagation. So yes, I remember that and there are some factor. For example, the true distance between the accelerator and the atomic cloud. So if I put the cloud a bit closer to the accelerator, then a larger fraction of particles can reach the cloud, and the required luminosity could be a few times lower. On the other hand, I want to see maybe this requirement is for energy budget is not that bad, because for like we have two jets, right? And each jet have a luminosity of a few times 10 to 39. So here, even if we take the total luminosity to be or proton to be 10 to 39, so it's maybe take like 50% energy goes into protons. I mean it's kind of extreme value, but you know, there are some kind of maybe 30%, 20%, 30% is sufficient. I mean, if the jet is a bit a few times 10 to 39.
And may I ask what's the energetics in the leptonic model?
Yeah.
May I ask what is the energetics in the leptonic model?
Leptonic model, so I mean here, in this fitting, or just, yeah, this I think for luminosity above 1 TeV is 10 to 30, a few times 10 to 35 arcs per second.
Mm-hmm.
Yeah, because the electron has higher radiation efficiency, and for protons, on one hand, the radiation efficiency is low, and also in this modeling, because many protons they do not reach the molecular cloud. They are diffusing in other direction, and they do not interacting with the cloud in that direction. So just a fraction, only a fraction of protons are interacting with them. So the total, so you need a quite large injection velocity, and only result in this low flux here.
Okay, thanks.
So I'm just going to have to say that I have to leave for another meeting. Ruoyu, thank you for an excellent talk. Paulo is going to complete the session. We have the room for the next 5 minutes. Susumu is next, but thank you very much.
Thank you, Rashmi. Thank you. Bye.
Thanks for you. Susumu, yeah, go ahead, Susumu. Yeah.
I mean, about the point that you were discussing now, I mean, doesn't this depend on what you assume for the diffusion coefficient in this region?
In this region, I assume a suppressed diffusion coefficient about I think it's kind of I don't remember the clear number, but it's kind of 2 orders of magnitude smaller than that.
It's already
standard SM. Yes, it's suppressed diffusion.
See. But I mean, is there a reason that it can't be even smaller than what you're assuming? I mean, yeah.
Well, I think it depends on the properties of the magnetic field in this region, because it's if it is within this, you know, this W50 I mean, WFE could be a super remnant, right? So if it's within a super remnant, in principle, I mean, if the turbulence is strong, then the diffusion coefficient could be quite small.
So if it is smaller, even smaller than what you assume, then you relieve the energetics further. No?
Yeah, then for sure, yes, yes. Then.
Because this was the point. I was actually waiting whether Felix might comment on this, but I realized that he's not here now today. So, but this was the point that, yeah, at the last meeting, Felix went on at quite some length, and it's a subject that Pasquale likes. But I guess it's a possibility to reduce the energetics.
Is it enough? Yeah.
Yeah. Okay. Thanks.
Thank you.
But is it really the transport dominated by diffusion, or is it rather expected to be dominated by advection, by motion?
Here I simply consider diffusion, the pure diffusion.
But why? I mean, if the diffusion coefficient is so small, even a relatively small motion of the plasma can easily transport the particles there.
Okay, yeah.
The smaller the diffusion coefficient, the easier it is for plasma bulk motion to transport the particles away.
I think that you mean kind of this MHD wave can advect the particles away.
Or even the motion of the particles, of the plasma, but just bulk motion, plasma motion. Like in the case of a wind, would be the wind motion.
Okay, then it depends on depends on how far the wind can reach, and actually it also depends on how far. I mean, how much is the true distance of this atomic cloud to the accelerator. So because what we see is just a projection, so there could be some distance in the in the direction of the line of sight. So if it is sufficiently far, I think in this modeling I assume it's like 50 per second from the black hole, and if this wind has not reached there, then maybe diffusion can still dominate the propagation. I mean, I actually don't have strong opinion on this. So as I said, this is just we just want to show an example that if you take some number, you can get this second component here with the hadronic arranging. Yeah, I mean, totally agree with you. This need to be a more specific, dedicated studies in the modeling in this region.
Yeah, for Pasquale. So I mean, if you have a wind and a jet, it's a pretty anisotropic magnetic field that change things, I guess.
Yeah, I guess. Yeah, I think Enrico, in this paper that you quote down here, I think Enrico was doing something similar, right? He was actually assuming that instead of a jet, you have a wind, and that you accelerate the particles at the termination shock. So in that case, for instance, you don't need to transport the particles from the center to the emission region. Particles are produced at the termination shock of the wind. So for instance, in that case, those considerations would not apply. And the transport of the particles, well, it depends on the conditions exactly. I'm not sure, but usually at the wind, the particles are transported mainly due to advection rather than diffusion, unless you go to very high energy. Yeah, I guess the bottom line is we should take these numbers with a grain of salt, because they really depend a lot on exactly where the particles are produced and what is the density in that blob, what is the diffusion coefficient in that blob, what's the advection velocity of the plasma, and so on and so forth. So I don't know.
Yeah, I totally agree with you. Yes.
Yeah. And maybe one related question had that. So the change in source geometry above like 100 TeV, that sort of means that it's not consistent with a termination shock because it seems more like central origin, or where's the cloud? Yeah, that's.
Yes. At least I think this indicates the change of the origin of the emission. But I'm not sure whether this can indicate the accelerator, because if this is a hadronic origin, then the morphology is also determined by where targets are. Yeah. So I think in this case, even particles are still if protons are accelerated in these two lobes, and they are propagated to this atomic cloud and illuminate this cloud. I mean, it could more or less result in same morphology, predictable morphology, to that if particles are accelerated at the center part, or accelerated. The recent paper by Parity et al. They consider this the disk wind driven shock disk wind bubble model from this around the center region. I think it's not easy to differentiate this different the acceleration sites.
Yeah, that's true. Good point. Yeah, thanks.
Thank you.
Maybe just for discussion purposes, like Andre Bikov, Andre, you have some model that's not so different. Do you agree about energetics and geometries and things like that?
Yes, our model was about two winds. One is more or less isotropic wind from the disk, and second is jet. And in our case, acceleration took place at the collision point where reclamation shocks appear. Then jet-like outflow actually collide with termination shock of isotropic wind. It's similar. And energetics is indeed an issue, but I don't think it is impossible to do.
Okay. In your model, what fraction of energy of the wind energy went into protons to make the luminosity? Was it high?
We arbitrarily assume what something like 10%, maybe a bit more, but not more.
No more.
In our case, it's again a hard spectrum. We are using multiple shocks, and so spectrum can be harder than 2.
Okay.
That actually alleviate the energetic problem usually.
Okay. Very interesting. All right, I'll have to go think. We'll all have to go think. Any other questions? We're coming up on past 10:30, so. All right. We can wait 30 seconds. Let's see.
Yeah, can I ask one more question?
Yeah, sure.
Concerning the model for cosmic rays, it is expected, if I understand correctly, that the other microquasars that produce the cosmic rays on Earth are nearer to us. So my question is, why don't we see them? They should be simply more powerful than these distant ones.
Well, I think one possibility is that they are active in past times, but not now.
I think.
Yeah, I mean, because the cosmic ray, they are delayed because they are transported in magnetic field, and photons can arrive very quickly, right? So this delay could be thousands of years or even longer time. Then probably I don't know. I mean, it also depends on how long is the period that this system can operate as a very extreme particle accelerator. For example, if let's say if SF433 can it lasts only for maybe several tens of thousand years and produce a lot of high energy particles, and these particles they may arrive at Earth maybe 1,000 years later, or even 10,000 years later, and maybe people at the time they can receive particles from SF433, but when they observe SF433 via light, it could be already faded away. I mean, disappear, something like that.
Yeah, sure.
So,
sure, I understand. But if you introduce a duty cycle like this, you have to introduce many more sources.
Yeah.
And, then the question is it consistent with other ideas on such sources?
Okay. Yeah, I see your point. So I think I cannot answer this question because I think it depends on how long this source can operate as the extreme particle accelerator. For example, if they can operate, keep this quite high particle injection efficiency for, let's say, million years, then probably we look at that direction, we still see a very bright emission in that direction. And in the meantime, we can receive particles accelerated from this source. But if the duration is only, let's say, 100,000 years or even 10,000 years, then when these particles arrive at Earth, they could disappear. So I mean, I'm not, I don't know. I think I cannot give you a clear answer to this because it highly depends on their properties.
Thank you.
Yeah.
Thank you for the question.
Maybe just relay that, and then we'll stop, I guess. But you need a lot more, because as he said, if the duty cycle is low, you need many nearby black hole systems, and maybe we don't know them. Of the sources you looked at, the 12 black holes, how many are closer than SS433? I should know this, but I don't. We don't have a complete survey of black hole LMXBs and HMXBs.
No. So now these 12 sources are selected in this way. So we have like these two are persistent source, and the other 10 they are transient source, and they kind of have this dynamical evidence for the black hole. And of course we have more black hole binary candidates. So far we have not checked these sources. So currently we are only choose the source in LHAASO field of view with kind of strong evidence for the black hole. Yeah, I think next step we can perform a more comprehensive examination of other black hole extra binary candidates, and we see whether we can detect some of them.
Mm-hmm. Yeah, it's a good idea. Okay. Any more questions? Let's see. As it's getting late. All right, since it's getting quite late, I actually have to go myself. So I think we're gonna sign off now. So Ruoyu, thank you very much for a great talk. You can see from all the discussion, this is very interesting and exciting. And let's hope there are more LHAASO results. Okay, so
thank you very much.
Okay, thanks everybody for coming. And as Rashmi said, in 2 weeks, December 11th, we're going to have a talk about more details about SS433, but from a sort of X-ray perspective, bringing in lots of different wavelengths. So that should be interesting too. Okay, see everybody. All right, thanks very much, and see you next time.
Yep. Bye.
Goodbye.
Bye. Thank you very much.
Bye.
Great. Thanks.
Bye.
Bye.